We were in chapter 4, one about the classification, second chapter on classification of robots. I think we talked a little bit more about geometry. Which would be let's see what's going on here. Oh. And we had two categories of methods of programming industrial robots. We have what's referred to as continuous path, and then we have what we call point-to-point. By far, the most widely used is point-to-point, because it's got quite a few more advantages. Some it's easy to program, and next, the programs are easy to edit. So what we do on a point-to-point robot is we come up and we, so this is the simulation of the Motorman robot over there, but it would be nice because I can record this. So what I'm going to do is I'm going to start a new program. So the first thing, one expected robot controller, select a job. So the first thing we have to do is we have to come up, when we create jobs on these, we have to come up with a name of the program. This is pretty common when you write programs. So this is normally the way we access things. So all these people that wrote all these programs for the personal computer or your iPhone came up with a name. Now, of course, the programs themselves are binary programs. We call it a language called machine language. And it's very, very complicated language to learn, which was one of the first programming languages that I learned was machine language programming for a 6800 Motorola microprocessor. And all these are binary codes that tells the computer what to do, or the processor what to do. Now what we do is we write programs in what we refer to as a high-level language, which is basically kind of like English, but we use a lot of acronyms and a lot of mnemonics inside the language. And then what we do is when we run the program, there's another machine language program inside the computer that translates it for us. So it allows us to write programs in a high-level language. Motorman uses a language called Inform 2. So all these programs out here, these are not programs, by the way. Most people turn the feature off because it doesn't make much sense to them. But the way we identify the names of programs is there's an extension put. We call it an extension. Most people turn this off. I'll get to it in a minute. But here's the program right here. So this little dot right here, an exe indicates that's actually a program. Data link libraries, these are modules that's used by programs, and then you have data that the program uses. And this is so if I go over here, and you look at these, you'll see no EXEs. But what you see is all these things that has the extension of of doc. Does that make sense? Y'all follow this so far? This is what we call a document file. This is, so every time you create a file, every time you name a file with like Office 2000 or Word or whatever word processor that you use. By the way, y'all know y'all can get Microsoft Office for free, right? Y'all know that? If you got a personal computer at home, it's called Office 365, but it's actually Office 10. All you need is just a lawful state email address. That's all it really requires when you sign up for it. So when you create a document, you've seen this before, one of the first things you got to do is give the document a name. And what it does is it attaches an extension on that thing that identifies it as a Microsoft Word document. And that's the extension right there. And then what we do is we set up and so I could load the Office EXE program and then load this in. But what we have the ability to do is we have the ability to set up what we call file associations. So one of the options right here is open with, and then we choose what application we want to open that extension with. Does that make sense? So now what I can do, instead of having to load the application, I can just come up here and double click on this one, and it's associated with this program, and it automatically loads that program in and loads the document. Does that make sense? So this is actually an application. Are you okay? So first thing we have to do, of course, is create a file name. Now this is going to give it the extension JBI, which is what this MotoSim application gives to its programs. And from then on, if I double click on any JBI file, it'll automatically load in this simulation software. So we've created our program, our file, and it automatically puts two instructions in here. It's a no operation and then an end, which tells the controller where the program actually is. And then what we do is we come up here, and this is a simulation of a teach pendant. And then we say, okay, we want to add a move. And what we do is we come up here, this is the moves available. And so we have three basic moves. We have what we call a joint move. And we specify speed, and we can specify what we call a round off, which we're not going to talk about right now. And then I can come up here, and when I enter this, it automatically enters that point into the program. So all the information that's relative to that point is stored in the program. Now we don't see that information, but this is the type of information that's actually stored. So I think this robot actually stores the encoder. So it saves this, and it tells the program where the location of all these different axes. And then what I can do is I can jog the robot. So here, and what we'll do is we'll jog it in what we call world mode. And this is XYZ. So XYZ, if I wanted to go down, I'll just come up here at -Z. And
XYZ representing the joint?
No, XYZ, we talked a little bit about this. What we can do with these robots is it's very complicated to figure out which joint to move. Okay. So we have the ability to jog the robot in what we call a Cartesian system. What's Cartesian? Sort of. Cartesian is a system where we can identify things by and we put this up several times, but this is pretty important to know, especially when you get into operation and programming. So Cartesian, first of all, we have three planes, and we call them X, Y, Z. One of them is a vertical plane, and what you have to do is you have to imagine this as a or a two-dimensional unit. So it's a vertical plane, and then we have a horizontal plane, and then we have a plane that comes in and out, and then we identify this with what we call an origin point of origin. And what you have to visualize is you have to visualize these planes as two-dimensional planes. And then what we can do is now so up and down, this is Z. So up this way would be what we call plus Z. And if I want the robot to go down, I can jog it minus it. If I want it to go right, then I'll jog plus Y. And if I want it to go to the left, I'll jog it minus Y. If I want it to come out, I'll jog it plus X. If I want it to go back, I'll minus X. So now when we jog the robot like this, we're not concerned about what axis to move. All I'm concerned about is a direction. Y'all understand that? I'm concerned with the direction. And this is a lot easier, so now I'm not saying, okay, do I need to move joint 1? Do I need to be joint 2? Do I need to be joint 3? I says, okay, what I want it to do is I want it to go down. Well, if I want it to go down, I'm going to go to inch. I'm going to go real slow. If I want it to go down, I just instead of figuring out what joint to move, I move. Oh, I'm sorry. If I want it to go down, I just say, okay, then I'm going to go down here. I'm going to go minus Z. Now look, it's moving multiple joints to maintain the orientation of the tool. But I'm not concerned in, okay, do I need to move joint 1? Do I need to move joint 2? Do I need to move joint 3? So Cartesian jog is probably one of the most popular ways to jog the robot. And then what I would do is I would come up here and I would say, okay, I'm going to come down here. And of course, it takes a lot to simulate opening and closing the gripper. But what I would do is I could come up here and I could come up here and I could move it over. Let's say I want to come down over the top of that. Well, now I want to go to the left, so I'm going to tell it to jog minus Y. See that? And then I want it to go down. Then I could, of course, I'm moving the work cell around. In real life, we would be doing what? We would be moving. And then what do I want to do now? I want to go plus X. Now, when I get the robot positioned where I want it to do, where I want it to be, then I would come up here and I would select what type of move, and we got 3. So what we're going to do here is I'll use what we call a straight line move. And then we come up here and we select the speed of the move, which is not one that I see if I key it in. And then we would say, we'll call it the round up. And then once I've decided how I want to move from the previous top point, I would just come up here and I would add that point. And then I would come up here and I would do something else. So let's swing it plus Y. And then I would come up here and I want to use the same move, I would teach that point. And then let's say I go minus Z. Sorry, plus Z. And then I teach this point. And then I want to swing it back over to basically the center. This is not really important. There's ways we can actually bring it back exactly the way it was. And then I would come up. What I'm going to do is go back to the last move here. And then I'm going to teach that. So what I just did is I taught the robot by moving it and telling the program to remember points. And then once I've got that, then I can come up here and then I can run the program. So this is what we call a point-to-point robot. And we have several ways that we can move between points. So what we do on a point-to-point robot is we jog the robot to a point within the Cartesian system. And then I decide what type of move do I want it to be. whether it's a linear move or a joint move or a circular move or a spline move. And that's what you'll learn in operation and programming, the different types of moves that you got available to you. And then, of course, we could do how much do we want to round off and all this other kind of stuff. There's a little more to it, but the actual command is basically stuck in there for you. So the syntax is there. Syntax, by the way, is the correct way of writing in a language, right? You understand that? So the syntax is put up there for you. All you got to do is go in and modify. All you got to do is go in there and modify what you want to do within that command.
What units are you using to do the X? So every time you hit that, it moves.
Yeah, over there it'd be a lot smoother. This is a simulation. I could hold it down, so if I come up here and hold it down, see it'll move smoother.
It rounds off.
No, round off is a method, and we don't need to talk much about this. But round off is a method where we can make the robot. So round off would be, okay, let's say I wanted to follow this path right here. Well, what we could do is I could teach a point there and teach a point there and teach a point up here. Now, normally, if we did it, you would think the robot would do this. But what we can do is we can specify a round off.
What I was thinking about is,
Well, we have two ways we can store. This robot uses what we call encoders, and we'll talk about encoders later on when we get into sensors. But what encoders do, and this is millimeters, by the way. So this would be right now. This is sitting at 4 millimeters, but then we have a fraction available too.
you could put 3.85.
Oh yeah, I could come up here now. We can't do this on the actual robot, but we can do this on a simulation. You know, I can come up here and I can say, okay, I want S to go 100 millimeters, and I hit enter, and by George, it moved. But it was hard to say. Another way, a lot of your robots do it according to the Cartesian system. So this means I moved X to 207.005 millimeters. Right now I'm sitting at 0.041 or 414 microns. Here it's 58.003 millimeters. So that's XYZ. And then the other three things we can specify is how much roll do we have. So this is roll. I'm sorry, this is yaw. This is pitch. And this is row. So we do have the ability to move the tool. And this is moving around something we call a tool center point. So that's what this guy right here is. This is the tool center point. We've already talked about tool center point, right? Yeah. Tool center point is the position that you're trying to go. What's nice about your simulation is you can put this wire diagram up here that shows you the exact location of the tool center point. So what roll, pitch, and yaw does is it jogs the robot around the tool center point. So notice the tool center point never moves. So it's actually doing this. So this would be yaw, this would be pitch, and then this right here would be roll. Roll basically never changes. By default though, so what we have is we have the tool center point set right there at the center.
Do you only refer to the optimal when the center point is?
When you're doing a Cartesian jog.
Okay.
A Cartesian jog would be what we call world jog or tool jog. If you're doing a joint jog, tool center point means nothing. The only thing the tool center point means when you do it, what we call a joint jog, is when it depends on the robot. So the Motorman robot stores these pulse readings right here. Just about all your other robots records the point in a XYZ roll pitch off. Or this one is.
You can get the degree of close.
Oh yeah, I mean, 'cause just think about this. This is millimeters, so this would be micrometers. That would be That would be 1,000 nanometers. So we have the ability to position this robot with the simulation within 1,000 nanometers. And that's but what I want you to see is, okay, this is the kind of stuff you'll learn if you take the operation and programming class, is how you jog the robot. You'll learn the different types of moves. But what I want you to see is that the way we program this robot is we teach points. And then according to what move I tell my program, this tells the controller how to move it from the previously taught point. And this is a point-to-point robot, and you can see how easy it is to program. All you got to do is learn what a linear move is, what a joint move is, what a circular move is, what a spline move is, and how do you round off, how do you make it cut the corners and that kind of stuff. And you can literally make a point-to-point robot follow any path you need to follow. But instead of me getting out there and grabbing this thing and moving around, so let's say I don't like that point. Okay, I don't like that point. Well, what I can do is I can come up here and just move it, and then I can tell this robot to modify the point, and I've changed the point. I can change the way it moves between the points. I can delete the point if I don't want it anymore. I can modify the point, or I can change the speed if I don't like it. I can change the round off if I don't like it. I could change it from a joint move to a linear move or whatever without doing what? Without going out there and moving that, and actually physically moving that robot around. And we call these point-to-point robots. These are by far the most widely used method of programming robots. Point-to-point robots.
That's what each time you get your arm, mathematics, you can move. Can they have the round off to it?
Yeah, but that's what you're doing. You're jogging it with this thing we call a teach pendant. Now there's a lot more to the teach pendant. So all these different menus and stuff I'm popping up are available on the teach pendant. All we get on the simulation is this on the teach pendant. And then I can use what we call so this is the actual position of the robot. Well, I've got a button on the teach pendant that I can look and see the position the robot's at. I can use the robot to make measurements for you. I can do things with the simulation that are really, really neat. So I can tell my simulation to find the top of this block. And then I can make my measurements according to the block. You know, so if I wanted to come up 15 millimeters, I could just come up and move this up 15 millimeters. So I would put this on 1, and then I would go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now I just did X at 15 millimeters. So over there it would be a little more difficult, but over there we would have to position the robot, we would have to touch it against something, then we would have to record that position, and then we would have to do a little bit of math. But a simulation is really, really neat. Plus what we can do with a simulation is we can set up what we call collision detection. Collision detection means if I screw up, something's going to turn red and say you screwed up. You get over there and you collide. Right over here, it's like playing a video game. You collide over here, it's not going to hurt you. So it's not going to hurt your $10,000 tool when you collide over here. Over there, if you was to collide that big old welder on the big Fanuc robot there, you know, telling how much that thing's, and the tips are copper, so they're a soft metal. They're a softer metal. You hit that thing against something, you knock it off just a hair, then your robot is going to be off a hair all the time, right? Does that make sense? So we can set up collision detection and all kind of neat stuff with the simulation. Over there, the only collision detection we got is when you collide with something. Well, what I want to do in this class is let you see what a point-to-point robot programming method is. Everybody okay? Now, the other guy that we have over here is we have the Lego robot. Now, the Lego robots is really neat in that we can set it up to program in what we call a continuous path. By leading it. Some people call these lead robots, but technically it's called a continuous path robot. And we got it set up to record for 30 seconds. Let's go ahead. I'm going to record it for 1 minute. So what I'm doing is I'm setting up, instead of me saying, instead of continuous path programming controller and robot, your memory is specified and how many minutes you can record. So we're setting it up for 1 minute. And then what I'm going to do is I'm going to download. Now these wheels are not really good and the resolution of the steering is not real good, but you'll get an idea of this anyway. So we're going to download this into the robot. Oh, duh. Okay. And the controller will beep at us when it tells us if the program is okay and it's okay to. And I'm gonna come up here and plug it back over to the camera. And here's this. That's it. And what we're gonna do is we're just gonna grab it and I'm gonna run the program. And then I'm just going to take the robot, I'm going to move it through a series of motions. Good idea of what it's doing. Not an average.
I'm not saying that. I'm saying it would.
A remote control car, according to it, it's got to have at least 3 axes, and also it's got what IRA calls a Class A model manually controlled. This is not manually controlled. I can manually control it. This is a well, for the I just programmed. So what I'm going to do is I'm going to come up here now. Of course, this you get the idea. You click there and slip it. But that's okay. You get the idea of what we're doing. So what I'm going to do is I'm going to change this over to play. And then I'm going to download it. Oh,
Sure.
someone put, I just told it to play back. Now I'm up here. I don't know how good this is coming up on the camera, guys. The best laid plan. I'll do a real short one this time. So, I think I went way past the limits. What happened? So we got it on record. We'll come up here and just
what I'll do, I'm just gonna push it back out. Just go ahead. And push it back.
So that was a really, really simple program. Worked great, Brian. And the motor.
Will that particular robot let you do Cartesian?
No, it's Cartesian would be X, Y, Z. So you have no Z on this robot because it can't go up and down. Can't do that. And it's just a car, so all you can do is turn it. Okay, understand. So continuous path has nothing to do with Cartesian. What continuous path does is you literally go out there and you grab the robot and you move it where you want it to go. You reposition the tool and everything while you're actually moving the robot through. Cartesian is a method of moving and jogging a robot, a point-to-point robot. So continuous path, there's not basically a Cartesian. Now it might save the points in Cartesian. So what a continuous path robot does is that we move it along a path, and the controller, depending on what they call a sample rate, it's still saving points, but it's doing it automatically. So I think the book comes up here, and it's a really good example in the textbook where they come up here and we want it to follow that. Well, what I would do is while I was grabbing and teaching it, the controller has what they call a sample rate, and what it's doing, it's recording all the axis on the robot automatically. And that's what a continuous path robot does. That makes sense? What a point-to-point robot would do is I would have to come up here and I would probably teach that point. I'd probably teach a point right there. I would teach a point right here. And this might be a circular move. This might be a linear move. This right here might be a circular move. And then I tell it how to move. As I program it, I tell it how to move. So this would be 1, 2, I'm sorry, I needed one right there. So that would be 1, 2, 3, 4, 5, 6, 7, 8 points that I would teach to teach that path right there. Well, what I do is I just grab the robot and I move it through here. So here I have to do what? I have to jog it to these points. Up here I do what? On a continuous path robot, I literally grab the robot and I move it through the path that I want it to follow. And then what happens is the controller literally does what? It has what they call a sample rate, where it comes up here and just saves 1,000 points. And here you don't have to do round off or anything because these points are so close together that it would make it smooth. That makes sense? So to do continuous path, what are you going to need? Well, one thing you're going to need is you're going to need a person that knows. You need some type of expert or whatever in what you're trying to do. So if I was going to use continuous path, the robot to program a painting robot, and I don't know how to paint, right? I don't know the technique for painting vehicles, then I wouldn't do any good, right? You understand? I don't know if you've ever seen somebody paint vehicles, but it's very imperative to maintain a constant speed, which the robot has no problem. You have to maintain a constant distance, and you have to do what they call an overlap. So what you do is you go one way, and then you do what? Then you come back. If you're not the painting robots that they use on the cars, they use what we call polarized paint. So really, the body of the car is charged to one potential, and then the paint's charged to the opposite potential. Then what do? They just clamp on each other. But if you've ever seen a person paint, it's not easy to do. Almost as easy as hard as welding. You get people that really know how to weld, they make it look easy till you get out there and try it yourself. Guys, I don't know why this thing's not recording, but I'll try to figure it out. I did say 1 minute, right? I bet I know what I did.
Maybe you should have done 1 point.
No, I think I said 1 second. That's true.
Yeah, you just put the number on there.
Yeah, so let's do record. And then time. Yeah, because originally it was set for 30, so that was 30 seconds. So that's what I did. So that's time in seconds. I knew I figured it out.
And like I said, we'll just go straight out and straight out from there.
So we'll download it into the robot, and then we'll teach it.
So what we do, programs don't turn with this guys. So we do that. And we'll do that.
That worked this time. Oh, darn it, you know what I just did? Yeah. Let's try it again. We'll switch it to play. So we'll see if it works this time. This little boy. Let's continue back. So what I do with continue path program, I literally lead the robot through what I want it to do, right? You understand? And then it comes back and runs that program. Of course, this is the only continuous path robot that we have the ability to do that. And like I said, later on we'll look at all these different tricks you can put out here to actually come in and program this, which it's really neat the way this programs. So this is the first one we'll look at. I don't know if we're going to have time to do the Hero robot, and I'm not really sure if it'll do what it needs to do anyway. So what else did we talk about in that chapter? Talked about different geometries, right? Which are very similar to envelopes or workspace. And the next thing,
Geometry, power, and
we looked at the geometry designators, the R's and the P's. Everybody okay there? Well, what's R indicate? The number of rotational axis, and P is the number of linear axis. P. You okay there? And then we talked about the Cartesian coordinates and the SCARA robot, which is pretty neat.
rotary and prismatic.
Yeah, prismatic. This is number of rotation axes. It should be rotational, I guess. And then prismatic. This basically deals with joints. Prismatic is a joint that is linear, a linear axis. So instead of using L, and why they decided to do that, they used P to indicate prismatic joint, linear joints, and we use R to represent rotational joints or rotary joints. So our robot would be a 6R. These robots right here.
Rotary.
Yeah. So these robots have 3 rotary axes. The only ones right now that we have, some of the robots on the line over there, we have 2 Ps over there. So it's got 1 horizontal axis and then 1 linear vertical axis. So that would be called what we call a 2P. We got a 1R over there, which would be close to not being actually a robot at all. It's got it's only got 1 rotational axis. No, I'm sorry, it's a 2R. It's got 2 rotational axes. But one of the rotational axes is controlled by mechanics. We'd have to go over there and look. I don't know if Brittany's doing her class over there up here. Are you okay there? Car robot, are you okay there? Selected compliance articulated robot arm. This is a cylindrical robot. Cylindrical articulated robot. And what do we mean by articulated when we talk about robot? So articulated on robot means you have multiple axes that are chained together with joints. That's what articulated means. And of course, the advantage of the SCAR robot is very simple. It usually has usually a 2R, but they're horizontal. And then we got at least 1 P. It might be a 3R. A lot of times what they do is they give the ability to rotate rotate it. You can't do roll, pitch, yaw with these guys, you know. That's why they're very popular with pick and place and assembly. So sometimes there'll be a 3R, sometimes there'll be a 3RP, or a P3R. That may be difference. And the spherical, and then we looked at a jointed spherical, which is what we have. They're also called anthropomorphic. I'll get that in a minute. What is anthropomorphic? Anthropomorphic means that it's something that is not human, that we use human terms to describe. So we call this an arm. So an arm is the term that we describe humans, right? A lot of times we call this a hand. We call this the wrist. We call that the shoulder. We call that the elbow. Well, those are human terms, but we're using it to describe something that is not human. And that's what the term anthropomorphic means. And by the way, the glossary, we update that glossary all semester long, so that's something you'll need to keep an eye on. Because it's, and then gantry crane. You okay on gantry cranes? Well, what's a gantry crane? There it is right there. These are robots that's mounted on a overhead positioning system, right? You understand? And what's the advantage of these guys? Yeah, less floor space. They take up space, but they take up less floor space is the difference. Which basically is what killed the World Trade Center. You know why the World Trade Center came down? Because all its structure was on the outside of the building. And it had open space. Well, it's kind of like this room right here. There was no beams or anything except for the elevator shafts inside all those floors. And people loved it because it gave them so much open space. But when they wiped out those, the side of the building, basically they lost the support for the floors. And what did the floors do? And they collapsed. Delta Robots, you okay there? We had one of these around here one time on loan, but unfortunately they came and got it back from us. And it's a point-to-point robot, and you teach it the same way. You can use the Cartesian system to jog it X, Y, Z, which is really, really neat. Depends on the other axis. And then we talked about the different types of power sources: hydraulic, pneumatic, and electric. And then, okay, we have a test about every 4 classes. The first one was, it's in the calendar. Why we have it every 4 classes, we got, 8 weeks. So we have 15 classes, or 14, depending on the holiday. I don't think we lose any classes for the holiday in this class, but Monday, Wednesday class, they didn't make up for that. So Monday, Wednesday classes, you got 4. So if we wait for the 5th class to give the first test, that means we have to have a test every 4 classes. And then this was point to point, and this is not exactly true. They did talk about a non-control path move. And then intelligence. That was all of chapter 4. Next chapter we'll go in. We're going to let y'all work on y'all's lab. Unfortunately, we've got a lot of people that's not here. But that's not our problem, right? You don't need to worry about those guys. The next thing we're going to lecture on is the next chapter. What's chapter 6? I'm sorry, 5. What's chapter 5? Yeah, work cell sensors. So here we'll try to arrange with Brittany so we can go over to the manufacturing line and look at a bunch of these sensors that the book actually teaches. We can teach it, but it's real neat to go and actually see them work, right? What does the sensor do? Anybody got an idea? You better know, Gary. Huh? Yeah, but sensors are just, what is our sensor do? So my brain has no idea what touch is. My brain has no idea what smell is. My brain has no idea what sight is. All it does is process chemical and electrical stuff. So a sensor takes a physical stimulus and converts it into something else. So in humans, it's either chemical or it's electrical. primarily being electrical, right? Of course, robots can't sense chemicals, so what do the sensors do for robotics? They convert a physical stimulus into an electrical quantity so the computer can process it, which is basically exactly what our sensors do, right? And we got a lot of them, guys. Even though we talk about the 5 senses, we have a lot of senses that are not part of the five senses.
Convert the physical stimulus what?
Into an electrical signal so it can be processed. And we'll look at later on. We have 2 basic categories, major categories. We call them analog and digital, and we'll look at those 2. But that'll be the next chapter. Y'all need to go ahead and start looking at chapter 5. So what we got going on today, y'all go ahead and take a 2-minute break, and we'll come back and make sure y'all know what y'all doing in lab. Thank you very much. Are you ready to play? Okay, we need to let you know when you're ready, all right? That's in the syllabus.